Okay, hi everyone. So if you guys want, turn your cameras on, but don't feel pressure to. It does make it a little more fun. And then the quick agenda is we'll be talking about Dijkstra's and A-star, MSTs, which will be Prims and Kruskals, and then we'll also be talking about graph algorithm design, which tends to be like some of the last questions on exams. Okay, with that in mind, let's get started. So I wanted to preface this by saying this review session is going to be on the challenging side. So if you guys aren't caught up in terms of the material, I recommend going back and reviewing the content, because we tend to build on that understanding level to do more creation questions and questions that are a little on the tougher side. So yes. Okay, the first one is Dijkstra's and A-star. And if you guys have any questions throughout, you guys can definitely interrupt me and then ask away. So the first problem, we start off with the classic shortest path tree from L. And then for the second part, we're going through each edge in the graph and asking, if I increase or decrease this edge by 2, does the shortest path tree change? Okay. So this is just a good Dijkstra's foundational question. I'll give you guys around, I'd say 8 minutes would be fair. Okay, hi everyone. We're going to go over questions 1 and 2. So I hope you guys thought it was a good starting question. Okay, so what edges are in the shortest path tree starting from L? When I approach Dijkstra's on an exam, I do it very intuitively. I don't actually write the priority queue or write any of that, I don't know, behind the scenes algorithm data structures. I just look at the graph and find the next closest vertex and then keep adding it to our shortest path tree. So we start at L, and then we say, who's the next closest? Let's go to U. Okay. And then at U, right, now we learn stuff about the neighbors of U, right? So we say, now who's the next closest? Let's go to T, right? Who's the next closest now? Let's go to E, right? Now who's the next closest? Well, it's a bit trickier, but we can see that I is currently 7 away, and A is currently 6 away. So let's go to A, right? And then we see that we'll go to I from here. And then we'll see that the next closest would be, we have M, which is 6, 9. Okay. Yes. And then we also have M and S are tied at 9 away because, oh wait, just kidding, just kidding. Haha. Okay. S is 8 away and M is 9 away, right? So the next person we'll get is S, and then we'll get M. But the order doesn't really matter. It's more about the final tree. Okay, so any questions here? Okay, so for this next part, what we're going to do is we're going to look at each edge, and we're going to say, if I increase it by 2 or decrease it by 2, will the shortest path tree change? Okay, so the first intuition is that if we have an edge that's blue, so if we have a blue edge, we should only consider increasing it by 2. Okay, if we have a gray edge, all we need to consider is decreasing it by 2. The reason is a blue edge is part of our shortest path tree, right? The only way to change the shortest path tree is by increasing it by 2. Because if I decrease it by 2, there's no way it's going to get removed from the shortest path tree, right? In the same light, if you look at all of the gray edges, right, this gray edge is only going to change anything if it somehow joins the shortest path tree. So we all need to consider is decreasing it by 2 so it could potentially join the shortest path tree. Okay, so my idea is let's look at all the blue edges and ask ourselves, if I increase it by 2, will the shortest path tree change? Right? Okay, so this is going to be a little mechanical. That was most of the intuition. So looking at UL, let's use a different color. We see that if I increase it by 2, let's just do them all right now. And then, okay, so looking at UL, if I increase it by 2, nothing's actually going to change. We're still going to use this blue edge in our shortest path tree, right? If I look at UT, I increase it by 2. nothing's going to change. We're still going to use UT in our shortest path tree, right? Okay. If I look at LE, nothing's going to change. We're still going to use LE because it's still the best way to get to E, right? Okay. So the first one that's actually going to change is now that this edge is 7, we see that getting to S via T is not as fast as getting to S via E, right? Do you guys see that? Because now this is 9 here, and if we got to S via T, it would be 1 plus 2 plus 5, which is 1 plus 2 plus 7, which is 10, right? Okay, so I'm going to create a list of edges. So we see here, the first one is TS. Okay. So I'm actually going to like do half and half. I'm going to do blue edges, and whenever I see a blue edge, I'll ask myself, what's the complementary gray edge that I could decrease to achieve the same result? Okay. So notice here that if I increase TS by 2, right, what happens is that this blue edge becomes like this, right? That's how the shortest path tree changes. In order to achieve the same change, we could also, right, take this 5 and decrease it to 3. Do you guys see that? In both ways, all we're doing is favoring this path, right? Okay, so TS and ES kind of complement each other. They both just change this blue edge at the bottom. Okay. So I'm just going to go back to the initial configuration. So let's look at AT and let's look at AI. Okay. So looking at AT, if I make it this purple, I realize a lot of purples make it confusing. So let's just look at 1. If I change this edge to 5, what we realize is that the shortest path to get to I is now via U, right? That is faster than going via A, right? So that's how it changes if we increase AT to 5. Okay, so we will put AT here. Okay, I'm sorry if this is boring. I'll try to make it a bit faster. So next for AI, if I increase AI by 2, we see that this is now 2, right? So now you guys are asking, like, does this actually change anything? Well, now getting to I is faster via UI than going this way. Okay? Because this is 7 on this path. And if we look at this path, it's now, I think, 8. Yeah. So this way is a total of 8 to get to I. Okay? So we see here that we can also change AI. And what we notice about both of the changes to AI and AT is that all they're doing is enabling UI to be part of the shortest path tree. Do you guys see that? So what we can do on the other side is we can enable UI to join the shortest path tree by decreasing 6 to 4, right? Because now what's going to happen is we find a better way to get to I, and then we'll lose, that was my bad, we'll lose this edge right here. Okay, so that's on the flip side. We can also decrease UI to 4. Okay, we're almost there. There's one last section at the end. So if we're looking at these two edges right here, you guys can notice that getting to M is marginally faster via A, right? It's only 1 faster. So it probably makes sense that if I increase this edge to 5, now it's not faster, because I'd rather go this way, right? In the same light, if I decrease 4 to 2, now we also see that it's faster to go the IM way, right? Okay, so we can add IM and AM. Okay, so these are all of the edges for part 2, and then the shortest path tree from part 1 is like this. Okay, any questions?
I have a question. So for the way we put TS into one of the edges, right? Because if we increase it by 2, it makes the pathway to S through E shorter. But if we increase UL or UT by 2, wouldn't that also, and like TS is unchanged, wouldn't that also increase the path from to S through U and T? And wouldn't that make E to S smaller?
Oh, wait, I think you're right. Yes, you're correct. You're correct. I missed that one. Good catch. Good catch. Yes, that's, yeah. So UT is one more. Let me think.
It'll be just any edge on the path right to S that we had
Yeah.
originally, right? Yeah.
Yeah. So now that's a good point. So one more I missed is UT. We can also increase that to 4. And what happens is that the path to T is still the best, but now getting to S is actually faster this way. Yeah. Good catch. And then in the same light, if we increase UL to 3, then we see that it's faster to get to ES. So those are 2 other ones I missed. Good catch. Okay. Any other questions? Nice. Okay, there's a lot of stuff in the chat. I completely missed the chat. Okay, hopefully it's resolved. Okay, I'll look at the chat. So are there any like actual questions that weren't resolved in chat? You guys can speak up. Otherwise, I'll like look at the chat when we move to the next part. Nice, okay. So the next one is A star. So for A star, we're going to define the heuristic of a given vertex as the shortest distance from that vertex to I. Okay? So the heuristic of T in this instance is, so the heuristic of T would be 3 because the shortest distance of T to I is 3. Okay? And the question is that if I, oh man, I did not mean to do that. If I is the end vertex, which vertex, when made the start vertex when we're running A star, would cause the most vertices to be visited? Okay? So, yeah. If you guys have any like confusion with the question, you guys can like speak up. Okay, so for the sake of time, I'm gonna go over it. I think a good amount of people had a chance by the participants tab. All right, so for this question, I wanna like have 2 main insights to start off with. So for the first insight is that when we have a heuristic where the heuristic of a vertex V is the actual shortest distance from V to the end, we can kind of think about this as like a perfect heuristic, right? Because most heuristics that we deal with are guesses at the actual shortest distance. But now we're dealing with a heuristic that's the actual shortest distance, right? So let's see like how that plays out. Okay, so the first thing I want to do is figure out the shortest distance from each one of these vertices to I. Okay, so what I'm going to do is just I'm going to create a shortest path tree rooted at I. And that'll help me figure out the shortest distance. So I'm going to quickly create a shortest path tree. Okay, so I quickly made a shortest path tree. So now each vertex, this is the shortest path tree rooted at I. Okay, so why is this helpful? Now we know the shortest distance from T to I is 3, right? The shortest distance from L to I is 6. Okay, so next to all of these vertices, let me just put their shortest distance. So, or their heuristic. M is 3, S is 8, E is 9, L is 6, U is 5, T is 3, A is 0. Okay, so let's just like try running A star from one of these vertices and see if anything cool comes up. Okay, I'm going to start from S. So if we're running A star from S, what we do is we put all of the vertices in the priority queue, right? So what happens is that we put E, T, and M in the priority queue. right? And what is the priority of all of these vertices? Well, it's the distance to E, right, plus the shortest distance from E to the goal, okay? So we see that E's priority is going to be 9 plus 5 equals 14, right? T's priority is going to be 5 plus 3 equals 8. M is going to be 9 plus 3 equals 12, okay? So as you guys probably guess, like, what we do is we go to T first, okay? But what's really cool with running A star with this perfect heuristic in this example is that we're going to keep continuing down this shortest path, okay? So if we start from S, we're only going to look at vertices on this shortest path, okay? I'll give you guys like a quick reason why, right? Let's ask ourselves, will we ever remove E from the priority queue? Well, we can't. Why not? Well, what's going to happen is after we remove T, right, what's going to happen is we'll replace T with the next vertex on the shortest path from S to I, right? So we'll add A to the priority queue, right? So after getting rid of T, right, A and some other vertices here will replace it, but A's priority will be 8, right? And what's cool about that is we know that this is the best priority any vertex in the queue could have, right? Because every other vertex isn't going on the shortest path. So we know that we first remove T, then we remove A, and then we finally remove I, right? So the order of removal, I'll write this down, order of removal for S is going to be T, then A, and then I, okay? And what you guys will notice is that these are the vertices on the shortest path from S to I. And the reason intuitively for that is since we're using a heuristic that's as good as possible, right? There's no need for us to consider vertices that aren't on the shortest path, okay? And the cool property about this graph is that all of the shortest paths are unique. There's not multiple shortest paths to get from one vertex to I. So since all of the shortest paths are unique, every time we run A star from any one of these vertices, we will only remove vertices on that shortest path, okay? So the question actually just comes down to which one of these vertices when made the start, has the most vertices on its shortest path, okay? So the question is which vertex is the most vertices away from I, right? The reason for this is that in order for L, which happens to be the one that's farthest away, right? When we run A star from L, we only are going to remove vertices U, T, A, right? We're only going to remove vertices on L's shortest path, which is the case for every vertex when it becomes the start with this perfect heuristic, okay? And what we can realize then is that L is the one that's the most vertices away from I, so L would be the vertex that would visit the most vertices. Okay, so this question is pretty tricky. Does anyone have any questions? Okay, so I don't understand. Okay, good question. So the question for like, just to reiterate for everyone else, is why can we ignore all of the other like edges? Like how do we have this like cool shortest paths property? Okay, so I'm gonna walk through us running A star from L, right? And hopefully like it'll make sense if we do one more iteration. Okay, so if we run A star from L, what's gonna happen is that U, T, and E will enter our priority queue with priorities. U's will be 6. And this is really cool. This is like the crux of this problem, is every path or every vertex on the shortest path from L to I will have the priority of the total cost of the shortest path. Okay, so I'll say that again. Every vertex on the shortest path has a priority that is equal to the cost of that shortest path. Okay, so let me just get rid of this. Has a priority equal to cost of shortest path, right? So with this in mind, what we can see is that we will have u in the priority queue, right? And nobody's going to have a priority better than 6, right? So what we'll do is we'll move u, then t's priority will get updated to 6. We'll remove t, then a will join with priority 6. We'll move a, then I joins with priority 6, right? We move I, and then we figure out the shortest. Then we figure out a star shortest path from L to I. Okay. Yes, this only works because of the perfect heuristic, as I called it. All right, so for the sake of time, I'll move on to the next question. If you guys have any questions about this one, you guys can voice them in the chat, and then I'll get to them. Okay, MSTs. Okay, so the first question is about prims. And I think it's good to just read it over. And if you guys have questions about the previous part, just ask me in the chat. Okay, so for part 1, the maximum number of times we could change the priority of a given vertex v is this thing called the degree of v. Okay, so I looked in lecture and you guys have seen the word degree before, but if you guys aren't familiar with what degree means, it's the number of neighbors a vertex v has. Okay, so you can also think about degree as the number of neighbors. Okay, and let me get rid of this. Okay, the reason for that is when we're executing prims, let's take the vertex b for example, right? We update the priority of a given vertex if we find a better way to connect that vertex to the MST, right? We update b upon finding, oh god, a better way, okay? So potentially every edge that's outgoing b gives us a better way to connect b to the MST, right? So since b has 2 outgoing edges, we could change the priority of b twice, right? And at minimum, since all vertices start off with priority infinity, we know that if the graph is connected, eventually every vertex must be part of the MST, so at minimum, its priority has to get changed once. Okay. So degree of v, number of neighbors v has, and 1, because eventually it has to join the MST. So we have to change it at least once. Okay. So yeah, with that in mind, take another couple minutes for parts 2 and 3. Okay, so we'll be going over parts 2 and 3, and I copy-pasted the same question onto 2 different slides, just for the case of space. Okay, so let's tackle parts A and B. I thought this question was kind of fun. I hope you guys enjoyed it. So we're running prims from A, and we want to fill in the missing edges on this graph, more specifically edges AC, BC, and CF, such that in part A, the priority of C is changed the maximum number of times, okay? And in part B, the priority of every vertex is changed the minimum number of times, okay? So when we're thinking about part A, what we want to have happen is that the priority of C is changed 4 times, okay? The reason the priority of C can be changed at maximum 4 times is because C has 4 edges going into it, okay? So what we want to have happen is that every time we look at another vertex that's neighboring C, we update our priority of C. So here's the big insight. Okay? We keep updating. Oh no. the priority of C. Sorry about the writing. Okay, so let's walk through prims and to see what's going to happen. So first we'll go at A, and I'll put the priority of C up here. It starts off at infinity. Okay, so we start off at A, and then what we do is we look at all the neighbors, right? That's the process of how prims, the Dijkstras work, right? We go to a vertex, we relax that vertex by looking at all the neighbors. So what we do is we see that C is this distance away, okay? And what we want to have happen is that for us to keep updating the priority of C, the first guess, or first like that priority of C should be a really big number, okay? So let's make this like some big number. We don't know what that is yet, totally fine, okay? So the next thing that we're going to do is we're going to go to the next closest vertex to our MST. So we will add G, okay? So after going to G, what we notice is that the priority of C has changed from infinity to the big number, and now it's going to change to 8, right? Because after going to G, we notice that C is 8 away, right? Okay, so we can fill in this big number now to be, how about 10? But it can be anything that's bigger than 8, right? So let's just put 10 here. Sure. Okay, so the next thing we're going to do is we will go to the next nearest vertex to join this MST, right? So we'll go to B. After going to B, what we need to do is update C, right, and improve on the previous priority. So what we should do is put maybe 7 here, right? Now, my bad. Then we'll go to F, right? And then F, finally, will update the priority of C for the final time. So let's put 6, okay? And then I just want to make it like in order. So we can do 9, 8, 7, 6, right? And then finally, what we'll notice is that we will add C to the MST using the CF edge. And the priority of C has been changed 4 times. Okay. Okay. Yeah, so just to like clarify, when we're running prims, we only consider the priority of a given vertex to be the edge between that vertex and somebody else, right? Because in Dijkstra's, what we do is the priority of a given vertex is the distance from that vertex to the start, right? In prims, the priority of a given vertex is a distance of that vertex to another vertex in the MST. Okay, so slight difference in priority. All right. Okay, so for the next part, we want the priority of a given vertex to be changed the minimum number of times. So all this is saying is that every time we see a vertex, we know that that's the best way to get to that vertex, okay? I like to think about is that prims doesn't ever have to update after the first update, right? We update once and then we're done. So after going to A, we see G, C, and B, and we set the values of G, C, and B in the priority queue, and we never change them, right? So for this to occur, let's just make C's priority, I don't know, let's make this edge 3. There's many possible solutions to this one, okay? So now what we want to have happen is that we're never going to change the priority of C or B or G, right? So let's just like, I don't know, go to G first, right? Then we'll see F is 4 away, right? So we put F as 4, okay? And then now we're basically done. We can just put 2 big numbers here, I don't know, 100, 101. And we see that we only changed the priority of every vertex once. Okay. Any questions? Okay, I'll answer Jane's question after I walk through Dijkstra's. I just have to think about it for like 20 seconds. And okay, so let's go over Dijkstra. So Dijkstra is a bit trickier, but it's the same idea from before. Okay, so in order for us to change C the maximum number of times, we keep finding a better way to get to C, right? So the insight, right, we keep finding a better way to get to C, right? So what that means is that we're first going to visit G, right? Actually, the first thing we'll do, I correct, is that we put C as an infinity. And then what we're going to do is set C's priority to be this number right here, which we can set as like some big number, right? Then C's priority is going to be 9. The reason it's 9 is now when we run Dijkstra's, it's the total distance on that path, right? Then what's going to happen is the next person we will visit is going to be B, right? So far we visited G, then we visit B, right? So after going to B, what we'll notice is that C's priority will be 2 plus, let's call this X, okay? Then what we're going to do is we want to visit C last, right? That's very important that we visit C last. So we want to visit F next, right? So we'll go to F, right? And then we'll put 5, right? Which is the distance to get to F, plus this edge weight, let's call that Y. Okay, so we see here that all of these numbers must be in decreasing order, right? If they're in decreasing order, then every time we update, it actually works, okay? So let's say that this big number, let's say that this starts off as 10, okay? So this will start off as 10. Then it goes to 9. Then it goes to, let's start off with Y. Let's make Y 1. Okay, now this sum is 6. So something in between, we could set X equal to 6, sure, right? Then this will be 8, right? 6, 8, 9, 10. That means we update every time, okay? And then any questions on that one? Nice. Actually, there seemed to be a question. So, good question. The first time, we're not actually updating. I would think about this as we're setting it in the beginning, right? So this is when we first add V to the priority queue, right? So we're not actually updating the priority. That's a different operation. We're just adding it to the priority queue with the given priority. So it's actually only 4 neighbors. Yeah, 4 updates, 1 addition. Okay. And then the next part is the priority of every vertex is changed the minimum number of times. Okay, so this is very similar to the last question, so I'll go a little fast. So intuitively, we just want all of these edges, right, to be such that every time we see a vertex, that's the best way of getting to that vertex, right? We never change our mind. So let's make this, I don't know, we can make C's 3. We just use the same example as last time, honestly. Right? We get to G, that's the best. Then we go to B, it's the best. Right? We go to C, it's the best. And then we go to F, right? And we only change every priority once. Okay. So just to reiterate, actually, I don't really want to reiterate. Okay, any questions? Yeah, it's 1. Okay. So yeah, let's move on to the next part then. Whew, okay. So Kruskals. Okay, so yeah, we have 2 parts. For the first part, now we know all of the edge weights are between 1 and 100, and we're wondering how does the runtime of Kruskals change, if any. Okay, and for the second part, now we don't have cycle detection, right? Recall when we usually run Kruskals, we have some way of telling us that the addition of this edge will create a cycle. Now, thinking about the possibility of what if we run Kruskals and we have no way of figuring out whether a cycle is created or not. So what we do instead is just add the first v minus 1 smallest edges, okay? And I'm wondering, will this work for the MST below? If it won't work, what's the edge or edges we need to change such that it will now work? And if you guys are trying to figure out a change, find the change that's the minimum added or removed weight. Okay? And then we break ties alphabetically. Okay. Yeah, go for that one. Okay, so I'll be going over both of these parts. I think these both are good questions to test you guys' like understanding of how Kruskals works. Okay, so when we're asking about any type of like runtime for an algorithm, we should first know how the runtime is actually like created, right? That's like a good foundation. So let's recall that the runtime of Kruskals, okay, can be split into two parts, okay? The first is sorting edges, okay? The second is adding edges to MST, right? This is how we can break up Kruskals runtime into two components. So when we sort the edges, usually we'll say E log E because that's how long a usual sorting algorithm takes, okay? And then adding edges to the MST, the reason this takes us time is because we have to store a weighted quick union, right, that processes if cycles are created, okay? So we have some sort of weighted quick union, and that's where the time complexity comes, okay? So this actually comes out to E log V, but when we take the sum of these two components, we notice that the first one dominates, right? Because E log E is always going to be bigger than E log V in any graph that's like not just a tree, right? We can usually think that this one is bigger, so we write the runtime of Kruskals as big O of E log E. But now, if we know that all of the edges are between 1 and 100, right? When we're sorting all of the edges, is there a better sorting algorithm to use, right? There is. We can use like an radix sort, LSD or MSD, right? Which will run in E time, because we know that the radix, right? If it's some number like this, it'll be an E time operation to sort E edges, okay? So now what we see is that the runtime of Kruskals changes to be E plus E log V. So the new runtime is going to be E log V. Okay? Any questions?
Wait, is there a difference between optimal and best?
So optimal is usually used in terms of like algorithms. Best is more like a hand wavy term, I'd say, but they're pretty similar. Does that seem fair? Yeah. And then is there a reason we don't use? So sometimes like an edge can have a weight that's like a decimal value, right? So oftentimes like we don't actually know how edges are compared. So it's good to just say E log E as just our way of like approaching the runtime, just because E log E is standard for any sorting algorithm. That's just why E log E is a default. So if we see an opportunity to like use radix sort, then we certainly can. So interesting. Okay. So the first question, so why can we assume that E is greater than V? Okay, that's in just the question. So the reason for this is suppose that E was as small as possible, right? If E was as small as possible, it would be V minus 1, right? In order for us to have like a graph where an MST would actually exist, we need at least V minus 1 edges in that MST, right? So we see here that in this case, the runtime is still E log E, right? Do you guys see that? That if E gets smaller, right, our runtime would just become E log V, which is the same as saying E log E, right? So even if E becomes small, the runtime can still be characterized by E log E. Because the difference between V minus 1 and V is like a constant. Okay, so generally though, when you guys like deal with any type of MST algorithm, the number of edges are generally much more than the number of vertices. Okay, but that weird edge case when e gets small is accounted for in the runtime. Yeah, okay, so in regards to like the weighted quick union asymptotics, you guys can just like assume that if we do some weighted quick union operation and we have like v vertices, it'll take log v time. Like you guys don't have to worry about like path compression unless we tell you guys. And we wouldn't ask you guys about the runtime of a path compression problem. That's a little out of scope. Okay. So let's move on to the next part. Okay. So this part's actually like sounds kind of scary, but it's not like too bad. You guys will soon see. So what I'm going to do is I'm just going to run Kruskals like usual until I try to add a cycle. Okay. So, right, in Kruskals, we just keep adding the shortest edge or the smallest edge. That's a better way of putting it. Okay. So Kruskals is fun. Okay. So now we get to the point where we can either add IM or EL. Right? And we know that EL is earlier than IM, so we would add EL. Yes, my alphabet skills are up to par, right? So now what we're left with is we're so close to creating that MST, right? All we need to do is add S, this lonely guy over here, to the MST. The problem right now is that on the current track, we're planning on adding this green edge right here, right? Which is a problem because we can't handle cycle detection. So what we need to do, there's a couple ways to remedy this, is we can either increase the weight of IM, right? If I make this guy 5, now we'll notice that we break ties and we will choose this edge. That's one solution. So I'll put that down. Solution 1 is increase IM by 1, right? And that's like basically the minimum possible change we could ever have, an increase by 1. Another change that we can do is we can also decrease ES by 1, right? That's another change. So solution 1, increase IM by 1. Solution 2 is decrease ES by 1. Okay. Any questions on this part? Nice. So I realize like we're not too efficient on time, so I'm going to skip this challenge problem. This is also like one of the hardest problems I've ever thought of. So if you guys have some free time and you guys are curious, try doing this question. It's pretty hard. It took me a while myself. So definitely recommend. It's a fun one. But for the sake of time, I'll skip it on this review session. Okay, exciting. Algorithm design. I allotted 40 minutes. We have 35. We will make do. Okay, so let's like quickly talk about algorithm design before we dive in. Okay. So when we approach any type of algorithm design problem, there's two main ways we can go about it. Okay. There's two main ways. Okay. So the first type of way we can approach it is we can modify the graph. Okay. So what that means is suppose we have some graph here. What are some possible ways I can modify it? Right? One way I can modify it is by adding nodes. Okay. Right? Let's say I add some D node that has some use somehow. Okay. Another way of modifying it is by changing edge weights. Okay. So there are other ways, but these are the two most popular ways of modifying a graph to achieve a new result. Okay. And we'll walk through some problems where you guys will see us actually utilizing these. Okay. So there's other ways, but these are the two most popular. So the other type of solution to an algorithm design problem, it comes from modifying the code. Okay, so what does this mean? Well, we all know that like Dijkstra's has some sort of pseudocode, MST prims, right? They all have pseudocode. So what I would do is write down pseudocode for these algorithms on your guys' cheat sheets so you guys are very familiar with the different steps in the algorithm, okay? Sometimes the solution may be to change this part of the algorithm to have this type of functionality, okay? So some problems may ask you guys, or may not, they're not going to necessarily ask, but a possible solution would be to change code from algorithms. Okay, some possible algorithms that are good to know are Dijkstra's, Prim's. Oh god, that's not how you spell Prim's. Kruskals, and then BFS, and then DFS. Okay, so yes, this is my 2-minute spiel on how to approach algorithm design questions. Okay, so with this in mind, let's dive in. So for the next, the remainder of this review session, I will give you guys some catch to running Dijkstra's, okay? So usually we can run Dijkstra's, everything works. I'm going to give you guys situations in which Dijkstra's alone won't work. What you guys will have to do is try to figure out how to modify the graph or modify the code of Dijkstra's such that we can go from U to V in E log V time. Okay? Some of these may not be intuitive, but I want you guys to spend some time and let's try things out. I think it's really fun. I also highly recommend, if you guys think of a solution that modifies the graph, try thinking about a solution that modifies the code, and vice versa. Challenge yourself to think of multiple ways to approach this problem. Okay? All right, this is fun. I hope you guys are excited. Go for it. Okay, so I'll be going over this first problem, and then hopefully it'll give you guys like some ideas of how to approach the later ones. Okay, so let's zoom in. Okay, so going off of this example, okay, I'm gonna approach two types of solutions to this problem, though they are like many more. Okay, so the first way will be modifying Dijkstra's. Okay, so if you guys recall, in Dijkstra's, we usually store this thing called distance 2, right? Which records the distance of that vertex to the start, okay? So now what I'm going to do is I'm going to change distance 2, and I'm going to make it cost 2v, okay? So what that's going to store is it's going to store the sum of edges plus sum of vertices, okay? We're just generalizing the distance 2 to make it cost 2v, okay? So now if you guys recall, in Dijkstra's, we update the distance 2 when we find a better way to get to a given vertex, right? So in Dijkstra's, we have this process called relaxing, where we look at a vertex, we say, I have found a better way to get to this vertex. Let me update the distance 2. Let me update the edge 2. So in relaxing, we're going to add, instead of updating the distance 2, all we need to do is update the cost 2, right? And that's going to be equal to, so let's say that we're considering the edge W to V, okay? So now what we're going to say is that the cost to get to V is going to be equal to cost to get to W, right, plus the edge weight of W and V plus the cost, actually let's call that weight, of V. Okay, this is how this would change, right? Usually in Dijkstra's, all we do is that we just say the distance to is equal to the distance to the neighbor plus the edge weight. Now we just add in this extra term, okay? So now what we're also going to have to do is that in the priority queue, right, in the priority queue, we usually use the priority as the distance to, right? Now all we have to do is change the priority to be the cost to, okay? So to recap, we changed the data structure we're using in Dijkstra's from distance to cost to, okay? And then all we're doing is that we're aggregating these costs, right? Okay, so that's one way. Let's go over the next way. The other way of approaching this is by modifying the graph. Okay, so modify graph. So let's look at this graph and see how we can modify it. Okay, so this is like maybe not an intuitive modification, but I think it's pretty cool. What we're going to do is we're going to take this undirected graph and we're going to make it directed. Okay, so for every edge, okay, for every edge, we will add 2 directed edges. Okay, so take this edge, AB, we will split it into 2 directed edges, right? That's essentially what an undirected edge is. Now what we're going to do is, in order to get to B, intuitively, we have to spend cost 1. Oh my god, that was massive, right? In order to get to B, we use cost 1 plus the weight of B. So to all incoming edges, add weight of V. Okay, so now if we look at, let's say that B's cost is 6, we take this edge 1 and we add 6 to it. Now what's going to happen is that in order to go to B, we use the edge weight 1 plus the cost of B. Okay, right? Let's look at C. And then A has cost 0 because it's the start. D has cost 0 since it's also the start. So in order to get to C, we have to do 3 plus the cost of C, which I think we said was 1. So what we'll do is this incoming edge is 3 plus 1, right? So now in order to get to C, we have a cost of 4, right? And what we can see is that if we change this, right, in order to get to C, it would be 4 plus 1, 5, right? If we change this for every edge on this graph, now when we run Dijkstra's, right, we can just run Dijkstra's as usual, and this graph is constructed so that the vertices don't have any cost anymore, but their cost, right, is put on the edges that are going into that vertex. Okay? Does that make sense?
I just had a quick question about why do we put the 2 edges, the directed one? Why don't we just add it to the undirected edges?
Yeah, really good question. So why do we need like this whole shebang of directed edges? So the problem is, suppose that we add the cost of B to all of B's outgoing edges. The problem that we see is now we're double counting the cost of going to B, right? If I say this is 1 plus 6 and this is 2 plus 6, now in order to go to B, right, we're doubling the actual cost because we're going 2 times that. So
But what if we only add it to the one going from A because it's our starting point and
interesting.
not to the other one?
Except like, let's say that we have like a really big graph and we have some random vertex in that graph. We don't know like how to get there, how to leave there, right? So it's hard for us to like say which is starting, which is ending, because this is a small example. If we have a really big graph, in a big graph, right, we might have some vertex somewhere that has unknown ways to get to, unknown ways to exit.
Oh, okay, I see. Thank you.
Yeah.
Why don't you have a direct path from B to D?
Oh, like over here?
Yeah.
It's because I was lazy and didn't finish the
Oh,
drawing.
okay.
Yes, that is totally my bad. So just to finish it, to get to B to D, we know that D has cost 0 since it's the goal. So we will put 2 plus 0, 2. D to B will be D8. But if you guys like think about it, intuitively this edge is like just there for the construction of the graph. It's actually like not needed because we're never going to exit the goal state. So if we want to be like, I don't know, marginally better, we could just ignore all outgoing edges from the goal state. Yeah, but for the sake of just going on this simple description. Okay, cool. Is it valid to change B into 7 nodes connected by 6 edges of weight 1? Yeah, so that would also work. But, okay, so let me present another solution. So modify part 2. Okay, so we'll make it a modified graph. So we'll say modified G. So what we can do is for any edge B, we still have to split it into a directed and undirected component. But what we'll do is, let's say B is of weight 7, and let's say it has these two edges, 1 and 3. We can break up B into B1 and B2 that are connected by an edge of weight 7, right? And then we'll put all incoming edges to B point to B1, right? And then outgoing like that, right? So in essence, you guys can see here that if we break up every vertex and we split it apart into these two components, now us going to B and out of B is the same in this new graph as us going to B1 and out of B2. That was massive. Okay, that's like another solution. I think this one's like a bit weirder though. No, it's not weird, I take that back. It's like kind of strange splitting up vertices. That's why I went with the other one, but it also works. Cool. Nice. All right. So let's move on to the next one. Okay. I'm not going to give you guys like too much time to think about it, sadly. I'll give you guys like around like 3 minutes and then I'll go over it. So next part. If we have two edges from U to V of the same cost, we want to choose the path with less edges. So quick example. Okay. So what this is saying is that if we have two edges of the same cost, let's say we have A, B, C, and D. Okay, this is 3, 1, 1, 1, right? So since both of these paths to get from A to B are the same weight, we would want to choose the path with less edges, right? Which would mean we would rather choose the AB path. But right now, Dijkstra's arbitrarily chooses between the two, right? Because we break ties like randomly as of now. So how can we change Dijkstra's such that we now break ties intelligently? Or yeah, any way you want to approach it. Doesn't have to be breaking ties. Okay, so we'll be walking through two possible solutions to this question. We'll go over how we can modify Dijkstra's and we can go over how we can modify the graph. Okay, so let's start off by modifying Dijkstra's. And I think all of these solutions are really, really cool. So if you guys are like watching this and you guys don't get it immediately, just like watch it and like think it's cool and it'll stick afterwards. Don't worry. Okay, so I copied the pseudocode because I realized it's kind of tough for you guys to like conceptualize if I just keep referring to some pseudocode. Okay, so if we recall, when we relax an edge in Dijkstra's, we only update the distance to if we see something is less than, right? But when we see two paths of equal cost, right, how do we deal with that? Well, let's add in a case here. So this should be an else if, actually. Else if the distance 2p plus w is equal to the distance to q, right? What that's saying is that the new distance is equal to the old distance, which is exactly what we're considering when we have two paths of the same cost, right? We need to have some way of breaking that tie. So what we should do is we should intuitively break ties. Or actually, this is not breaking ties. I'm going to correct myself. This is more of like we find two paths of equal cost. How do we choose which one to take? So choose option with less edges, right? So in order to like choose the option with less edges, we probably need to store some sort of data structure. Let's call it like num edges that takes in vertices and maps them to an int, right? So this is going to be some sort of map, which will map each vertex to the number of, let's call that, yeah, the number of edges on the path. So in this example right here, we could put D, right? And it has two edges, okay? So we would see in num edges, we would have the entry D:2, right? Because when we added D, right, we also updated the number of edges we took to get to D, right? So all we need to do is keep track of this data structure, num edges, which we will update, right, along with the other relaxing operations, right? So every time we like find a better way to get to a vertex, we update the num edges, this data structure, right? That's one thing we need to do. The second is we add this else if check to see if we find two paths of equal cost, we will use num edges as that way of figuring out which path to choose, okay? And then num edges. Okay, so this is like kind of hand wavy. So in an exam setting, you guys would probably be a bit more rigorous. So yes, that is the changes if we want to modify Dijkstra's. Okay. Okay, we're almost there. This one's really, really cool. So the next way is what if we can modify the graph? Okay. So looking at this graph, what if we add a really small number to every edge? Okay. So let's make this 1.001, 0.001. Okay. This is my idea. And let's make this 3.001. Okay. So now what you guys notice, this is like pretty cool, is that we will choose the top path because it barely beats this bottom path, right? Because 3.003 is greater than 3.001, right? So you guys can see by adding this small constant to every edge, we are now favoring paths with less edges, which is exactly what the problem states. The only catch, which is really, really hard to see, is that we can't add a random number because what happens if the graph is huge, right? So we should add a number that's proportional to n. So we should add something that's proportional to n, okay? The reason for that is whenever we deal with these large graphs, this small constant, if it gets added so many times, like let's say we add it, I don't know, like 1,000,000 times, eventually it'll exceed 1 and we may take a wrong path, okay? So the slight problem that we see is that if we have a fixed constant, we could potentially compromise the integrity of Dijkstra's by choosing a path that's not actually the best, right? So the idea here is that this number that we add should be proportional to the number of vertices in the graph. Okay, so the solution, which is remarkably slick and simple, is we will add 1 over n, where n is the number of vertices, to each edge. Okay. If you guys want to like make it really clear, we can do n squared, right? As long as it's some small constant that's proportional to the number of vertices in the graph, right? Because if we add this small number to every single edge and all of the edges are integers, this is only used for the equal tie-breaking case, right? Okay, I think that's pretty cool. So that's the solution if we want to modify G, the graph. Okay, questions? Okay, so sadly, we're like almost out of time. I'm probably going to stay after because I really like the remaining questions. If you guys want, like, you guys can feel free to drop off at 6. Otherwise, for everyone who's like interested in finishing the last 3 subparts, feel free to stick around. This is recorded, so you guys can just watch the recording afterwards. But I think this part is like pretty good. So let's ask some questions. If you guys have a question, like ask out loud. So it's more fun for me.
Wait, so
Yeah.
do you mind defining cost really quick?
Yeah. Okay, so the cost is, okay, so when I say the cost, I think I've said that a lot. That's my bad. That's like the total weight of a given path. Okay, so we can define the cost is equal to the total weight of a path. Does that clear things up?
Yeah, it does. So does that mean that you would have to like pre-calculate cost before you run the algorithm?
Oh. Okay. We don't have to like pre-calculate the cost. Is there, so like, I think I might have made some of these steps confusing. Were there any like steps that I could like re-explain?
Like, how would you know that like the A to C, C to D, D to B is immediately like worse than A to B? Like, are you calculating costs along the way, or are you like pre-calculating costs and then running the algorithm to determine which path to pick?
Okay. So in the beginning, we add 1 over n squared to each edge. Okay. So now all of the edge weights have changed, and all we do now is just run Dijkstra's.
Got it. Okay.
And then beautifully it'll work. Yeah.
Okay, that makes sense. I was like, yeah, if we're like predetermining the cost for each iteration, that's going to increase the runtime by a lot, but that makes a lot of sense. Thank you.
Yeah. Good clarification. Okay. Any other questions? Yeah, so the beauty is that since we're only adding a really small number, all that small number is doing is that if we have 2 paths of the same cost, it's like that tiebreaker, right? But for other paths, if one path is better than another path, it's not going to do anything, right? Because if one path is better than another path, it must be at least 1, like the number 1, more than the other path, okay? In which case, all of these small 1 over n squared terms will never be enough to make a bad path better than the optimal one. Yeah, pretty cool. I really like this. All right. So any other questions? Okay. So the next graph algorithm design. And I really recommend, if you guys keep doing a lot of these questions, you guys will learn little tools. And if you guys just write down all of these little tools to approach these problems, they'll be a lot more manageable, right? All of these problems just have like a toolkit. And if you guys know what that toolkit is, it's way easier to approach. So take like notes on the ways that I've solved these, because I think it's pretty helpful. Okay, so I'm just gonna go over this one. It's actually not like as bad as the other ones, so I don't want you guys to like overthink it. So there's 2 main ways that we could approach this. So 2 solutions. The first is that we modify the graph. Okay, and what we're going to do is remove bad edges. Okay, so we'll define an edge as being bad if it is not going from k to k plus 1, right? For all k. Okay, so if we have like some edge that's like 3 to 5, we can just remove it, right? And then we can just run Dijkstra's. The other way is we modify Dijkstra's. Okay, so now when we're looking at neighbors, we exclude neighbors that are bad, right? Because in Dijkstra's, we look at all the neighbors. So we just find a neighbor that's invalid. We just move on, right? So this one wasn't like too tricky, I hope, but what do we have to graph? I see. So for the first solution, it could be like in any ordering. Oh, actually, yes, we would have to make the graph directed. Yes. Yes, that's my bad. So remove bad edges and directed. Okay. So good catch. Yeah, we have to make the graph directed. So the reason for making it directed is that we can go from like k to k plus 1. So we should only have like edges in that directed ordering. Okay. So good catch. Okay. Any questions about this one?
I had a weird question, but like for another solution, because like it's like the subsets are like partition for like each
Yeah.
vertex is like a subset. Could we like maybe like add an edge to vertexes that are like connected to each other and give it like a ridiculously like high weight or something? So like if we run Dijkstra's, it just wouldn't go there because it's just like too big of a number, like something like that.
Wait, what do you mean by like adding weights to which edges?
Oh, so let's say we're trying to go from like A to B, and C is partition, right? It's a partition with C.
Yeah.
So we can just add like a high number to that edge connecting it. So like when we run Dijkstra's, it just wouldn't go there.
Yeah, that could also work if we add like really high, weights. But then you'd have to add something that's proportionally high, right?
Yeah.
It'd have to be proportional with the graph. Yeah. Nice. Okay. So let's move on to the next one. Okay. So for this one, now we're trying to get from U to V, and we have to go through vertices S and K. So let's just say that somewhere here there's S, somewhere here that's K. So our path has to go through S, right? This has to hit S and K on the path. Okay. Okay, so some people like had some idea. So I'll just like go ahead and give the solution. So the idea here is that we can run Dijkstra's multiple times. Okay. And if I run it a constant number of times, like let's say I run Dijkstra's k times, right? Then it'll just be E log V. Assuming that like k is like a number like, I don't know, like 3 or 5, right? So the easiest way that we could approach it is that we could run Dijkstra's from like everywhere, right? Like let me just run Dijkstra's from U, S, K, and V, because these are like the places we want, right? Like that's one way of going about it. Okay, so let's say idea 1. Let's make this a bit smaller first. No, this should work. Okay, so idea 1 is run Dijkstra's from U, V, S, and K. Okay, so that's like one possible way, but in this class, like we can make it a bit more efficient, right? So let's try to figure out, we don't need to run it from all of these places. All we need to do is run it from S and run it from K. Okay, so solution is run Dijkstra's from S and K. Okay, so what that's going to give us is we will have the shortest path from S to U, S to V, and S to K. In the same light, we will have the shortest path from K to S, K to V, and K to U, right? Right, we get all of these purple and red edges. So with this, all we really need to do is we know that going from U to V must go through S and K. So we could take the minimum, right, of this option, and the other option is U, K, S, V, right? So we just look at both possibilities from getting from U to V. We can either go to S first, then K, and then V, or K, S, and then V. And then for each one of these little pieces here, we will use the corresponding shortest path, right? From U to S, we will use this path right here. S to K, right? We computed that twice. K to V is this right here, right? In the same light, we have U to K, and then K to S, and then S to V, right? K to S, and then S to V, right? And then we just take the minimum of both possibilities. Okay, so this is like written not too nicely, but I think hopefully the intuition is there. Any questions? Nice. Okay, oh, question. So for runtime, it's actually not that bad. It's just 3 times E log V. The question is like, what happens if we run Dijkstra's 3 or 4 times? It'll be like 3 times E log V, which just becomes E log V, because that's how asymptotics works. Okay, so this is the last one, I promise. I think this one is kind of cool. The last two were, I think, a bit easier than the first one, but this one will have you guys think for a bit. Okay, so the idea here is instead of starting from U and ending at V, we could start from any vertex in some subset. So let's say these are all potential starting points. Okay, and we can finish in any subset. Okay, so these are all the finishing. Okay, so what you guys need to do is figure out the best starting vertex and the best finishing vertex and the optimal path. Right? Nice, cool. Let's do it. Okay, I think we all want to go, so let's finish this. You guys made it this far. Okay. Hopefully you guys had like an aha moment when you guys didn't get the solution, then saw the percolation hint, and then got the solution. Did anyone like actually get the percolation aha? Oh no. Yes, okay, one person. Phew, okay. I thought it was a cool connection. Okay, so what is this percolation thing he is talking about? In percolation, what you guys probably did is you guys made a starting dummy node, right? And you guys also made a dummy node at the end, right? And what we did in percolation, which was pretty clever at the time, was that we connected this dummy node to everybody at that top layer, right? All of like the, I don't know, grass people, we connected the dummy node to, which we can do here. So let's connect the dummy node to everyone in this starting subset, right? And we will do so with an edge of cost 0, right? Because we want the dummy node to not incur any cost from going from one place to another place, right? In the same light, what we'll do is take this end dummy node and connect it to all of the end components. And then we're basically just running percolation, right? We're just running Dijkstras from the dummy node to the end, which is, I think, pretty similar to how you guys ran percolation. So yeah, pretty cool. To recap, start, dummy node, and end, dummy node, right? Then we run. Actually, then we connect, start, dummy, to all starting subset vertices. And then in the same light, we connect the end dummy to all ending end set vertices. Okay, and then we run Dijkstras. Okay, so that's all I had for this review session. Thank you guys for staying this long. I really appreciate it. And it's been a good semester for all the people that have come out to my discussion, or people who have seen me like around. I really enjoyed teaching 61B. I hope you guys enjoyed the class. So yeah, congratulations for finishing, and reach out to me like anytime. If you guys have any questions about like teaching, about CS in general, I'm definitely down to talk.